Hello students, welcome back. We're going to continue today with proteins part 4 and what we've learned so far. Let's see what we've learned about proteins so far. Let's see what we have here. Okay, we learned about the different types of proteins. That's more types of proteins. Let's see, this is what I want to get to here. Yes, okay. If you have some tissue here, like a muscle, and you want to get the protein out of that muscle, you want to grind it up in some sort of buffer and then filter it to get your tissue fluid. And now you want to precipitate the protein away from the other components. And so the first thing you do is put the protein at its isoelectric point. That's going to promote precipitation of the proteins. But the proteins may not precipitate here. And so what you want to do then is place those proteins in a very high salt concentration, something like 4 molar or higher. And so when you put it in very high salt, all of the hydrogen bonds of the water will be taken up by the salt, and then the proteins will be left to themselves. They will clump together and fall out of solution. They'll precipitate. Actually, they'll just make the solution cloudy, and then you'll spin that down on a centrifuge, and the proteins will all go to the bottom. And so now, in this I was just explaining that. So we have our protein precipitate. Now let's continue today. What can we do with that protein precipitate? Okay, now once the proteins have precipitated, now you can redissolve the protein in some sort of PBS buffer. So, okay, let's put that here. Well, I need to go from here. So I'm just going to start from here. And so here we're going to have our protein in a solution. Okay. Okay, and what's going to happen? Now this protein solution is going to be really cloudy. It's just going to be a really cloudy protein solution. That's what you're going to have. A really cloudy solution of proteins. It's forming a precipitate. Now you will take, I'll just put here cloudy, oh, that color's not going to work. Bless you. Cloudy proteins. Okay, your proteins are going to be kind of cloudy here. And then what you'll do, you'll take a centrifuge here. Everybody know what a centrifuge looks like. Okay, you'll take this centrifuge and you'll spin this solution down, or this mixture down. Well, I'll just redraw it. It's going to be easy. And then what you're going to have, then all your proteins will then go to the bottom. Exactly. And that's called, and the solid part at the bottom, this is called the pellet at the bottom. That's good. You all know that. Does anybody have any idea what the liquid is called on top? Very good, the supernatant. So you have the pellet at the bottom and the supernatant at the top. And the supernatant has the high salt. And so what you want to do now is pour off that high salt and redissolve the pellet. Okay, and you're going to redissolve that pellet here. I'll put here redissolve pellet. Okay, and what would you want to redissolve this pellet in? What would be a good? What do we want to redissolve this pellet in? Not water. Buffer. What type of buffer would be good? What buffer? I can hear you. Okay. Oh, okay. It would have a weak. The buffer would have a weak acid. But what buffer have we made that has a weak acid in it? No, that's a base. Yeah. What buffer? What do we call that buffer? What was that again? PBS buffer. Exactly. And so we dissolve it on a PBS buffer would be great. Okay. And then your protein is going to be in solution. Your protein is going to be redissolved now. Okay. Now what we want to do, now we have all of the proteins are in this solution, but we don't want all the. Let's say we just want one protein, one globular protein, and so now we need to come up with a way to separate the protein that we want from all the other proteins. Make sense? Are we ready to do? And so that's what I'm gonna do today in class. I'm gonna explain how we're gonna get the protein we want away from all the other proteins. Let's just choose name any globular protein. It doesn't matter. Tyrosine hydroxylase. Okay, let's say tyrosine hydroxylase and all the other proteins that are in muscle are here. And so we want to get tyrosine hydroxylase. Everyone with me so far? Okay. Now, this is how we do that. And so, let's see here. We're going to have I'm just going to put a lot of proteins. Okay, we'll put protein P, protein W, protein X, protein Y, and protein Z. Okay. And let's say that some of these proteins have a net positive charge, some of them have a net negative charge. Okay, and so let's do this. Let's make that one negative, make this one negative, and make this one negative. And then we'll have three other proteins, A, B, and C, and we'll make them positive. So we have lots of different proteins. But let's say the one we want is P minus. P minus is the one we want. And so at a pH of 7.4, some of the proteins are positively charged, some of the proteins are negatively charged. Some of them are neutral there. Okay. So now, how are we going to separate our P protein from the others? Now, since this protein has a negative charge, we can do something special. Now, before I explain the concept by drawing, I'm just going to explain it to you. Just see if this makes sense to you. Since this protein has a negative charge, what if we could make some sort of substance that had a positive charge? And we could run all of our proteins over this substance. And now the proteins that have a negative charge would stick, and all the other proteins would just keep going past. Does that concept make sense before I explain it? Does that make sense? So we're going to have a substance that has a positive charge. We're going to pass all of these proteins over that positively charged substance. Everything that's negatively charged is going to bind to that substance, and everything that has a positive charge or no charge, they're going to pass through. And so in that way, we can separate our protein or all the negatively charged proteins from everything else. Does that make sense before I explain how it works? Okay, excellent. So let's do that now. Okay. Now what we're going to do, we're going to take these small little beads here, and let's say here, this is a bead here, and those beads are going to have positive charges attached to them. They're going to have positive charges attached to them. And now what we're going to do, we're going to make a big, we're going to have a big column here. And this column is just going to be filled with these beads with all of these positive charges. Okay, I'm just going to draw. There are millions of them, but I'm just going to draw a few of them. So there's a bead with a positive charge here. Here's a bead here with a positive charge. And here's a bead here with a positive charge. I'm only drawing 3, but there are millions of them. Everybody okay with this? Now let's take our protein solution. I'm just going to get it from this page here, so I won't have to redraw it again. Okay. Okay. Now here's our protein solution. Now we're going to add that entire solution to this column here. And so when you add these proteins to this solution, we're going to have, let's see what proteins, or I know what, you all can tell me. Okay, let's look and see. Let's just zoom in on this solution and see if you understand this. Which of these proteins will stick to this column? Look at the chart here. Okay, we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 different types of proteins here. P, W, X, A, B, C, Y, Z. Which of these proteins will stick to the beads? P will. P, Y, and X. Who disagrees with this? Nobody disagrees? Because you're right. Exactly. It makes sense. P, Y, and X are going to stick to the column because they have a negative charge. So you have to understand that. So what's going to happen here? You're going to have, let me go here. I'm on the wrong layer. Let's see here. So when you put this on the column, P is going to stick to the column. Y minus is going to stick to the column, and X minus will stick to the column. What's going to happen to all of those other proteins? They're going to just pass right through. So what's going to pass through? A, B, C, W, Z. So here, let's say you collect what passes through. Okay. And so what's going to pass through, you're going to have A plus B plus C plus W with no charge, and Z with no charge. All of those are going to pass through the column. And so we'll move this to the side here. So A, B, C, W, and Z, they're going to pass through the column. And so now you'll move that out the way. Now we have only the negatively charged proteins are on the column. Make sense? Now, how are we going to get those negatively charged proteins off the column? We want to use them. Yes, okay, we want to make them dissociate. How do we make them dissociate from the column? How do we get these proteins off of this column? Okay, but they're already in buffer. They're already in PBS buffer. Remember, we redissolved it. But what did you say before that? Okay, now if you add a base to something, is that going to cause, will bases cause something to dissociate or associate? Okay, it will cause an acid to dissociate. And so if an acid is, like if you have COOH and you add a high base, it's going to cause dissociation. You're going to have H plus, and then you're going to have the negatively charged, amino acid. And so we already have negative charges. So adding a base wouldn't help us, because bases make things really negative, because it causes the proton to go away. Exactly. So if you, right, we could do either one of those. Exactly. If you make the solution acidic, then all of these negative charges on the amino acids would have to take their protons back. Now they won't be negatively charged anymore, and now they'll come out of the column. Make sense? So that's one way we could do it. We could make the solution acidic. So getting something that's stuck to a column off of the column, that process has a special name. I'm going to give you that name first. So if you want to get something off of a column, you want to elute it. So the process of removing something from the column is called elution. So we want to elute the protein from the column, and that's called elution. Now we can do that in several ways, as you all have mentioned. We can add acid. We can add our same buffer, or we can just make a buffer at a very acidic pH. So we can add acid, and that's going to cause those protons to go back onto the protein. Now the protein doesn't have a positive charge, negative charge. Now the protein will come out. That's one way. But the most common way that people do this is to just add a very high salt concentration. And it could be any salt. And what's going to happen? The anions in the salt are going to add themselves to the positive charge. Now the protein can't stick there anymore because we have so many anions. So you can add high salt. And so when you add high salt, the anion that you add is going to displace the negatively charged proteins. And so what you're doing, so if this protein is negatively charged, it's an anion. And so when you add high salt, you'll just replace one anion for another anion. Does the concept make sense? Shelby, make sense? Yeah, let's explain that again here. Okay, let's just start at the beginning. So you have here yourself. I'm going to get rid of my proteins if I can. Okay. So you have yourself and I'm going to get rid of this and this. Okay. You have yourself a solution here that has different types of proteins. Some of the proteins are anionic, which means they have a negative charge. Some of the proteins are cationic, which have a positive charge. And some of the proteins are neutral. You're going to add these proteins here. You're going to add that entire solution onto this column. And when you add them onto the column, which proteins are going to stick to the column? Which proteins are going to stick to the column? Which proteins? The anions, exactly. And so you have three anions. You have P minus, Y minus, and X minus. And so all of these are going to stick to the column because they have different charges. Does that part make sense first? Okay, now, and so what's going to happen to all of these other proteins? What's going to happen to A plus, B plus, C plus, W, and Z? What's going to happen to those? They're just going to pass on through the column. They're going to be held by anything. And so they're going to pass through the column, and you're going to have them here. And so those will pass straight through. Now, we have our anionic proteins are on the column. We want to get them off of the column. We can do it in one of two ways. We could make this solution, we could make the column, we could add a very acidic buffer, which people don't normally do it that way. Or you can add a high salt and let the anions in the salt displace the protein anions. And then when you do that, for example, let's say here we add a salt here, NaCl. So we won't worry about the Cl right now, but the Na, but the Cl, that's what we really care about. And so here, when you add a really high salt concentration, let's say NaCl. And so when you do this, now the Cl, if you have a lot of Cl, the Cl minus is going to bind to that positive charge. And here the Cl minus is going to bind to this positive charge. And here the Cl minus anion is going to bind to this positive charge. And when that happens, let's see if I can find the protein. There we are. Then the protein will be released. And now your proteins are going to be, you're going to elute your proteins from the column. So you're going to have P minus, X minus, and what was the other one? Y minus, Y minus. Then your proteins will come out. And now what you've done, you've exchanged one anion for another anion. You've exchanged the protein anions for the chloride anions. Question? Now the sodiums, because when you're in water, sodium is a strong electrolyte, so it never attaches. Anions, salts just dissociate completely in water. And so it's not really these chlorides here are just going to basically displace. There's going to be an equilibrium. They're going to displace those negatively charged proteins from the positive charge on those beads. And when it keeps displacing them, those proteins will start moving down on the column because they'll be releasing and attaching, because there's an equilibrium that takes place. But because there are so many chlorides, they're gonna be off enough, and so eventually they're gonna come off of the column. They're gonna pass through the column. Exactly. But again, you have to think about it this way. There's an equilibrium that takes place. And so if you have something like this, if you have sodium chloride, you put sodium chloride in water, NaCl, and you put it in water, you're going to have Na plus Cl minus. Now what's going to happen here, this is an equilibrium because you have two arrows. But the thing is, there's going to be an extremely large amount of this in the solution because sodium chloride is a strong electrolyte. But there will be a little of this. There's a little attachment that takes place, but not a lot. But now what's going to happen when you put this sodium chloride in the water? There's going to be a little attachment of the sodium chloride to those positively charged beads. But that little is going to be enough to get the proteins off for just a second. And when those proteins come off for a second, then they're going to move down the column. Then they may stick to another bead, but because there's so much chloride around, they're going to come off, and they're going to go down a little. And eventually those proteins, those anionic proteins, are going to eventually come off of that column. You just have to remember, there's an equilibrium that takes place. Even for strong electrolytes, there is some non-dissociation. Okay, now what the sodium is going to do is going to have a positive charge, and so because these are positively charged here, it's not going to stick to the column. It could do one of two things. The sodium is going to be in equilibrium here with the chloride, and so those that are just like this, they'll just pass through the column. It's going to be in equilibrium here, completely dissociated from the chloride, and there's one more, and her question was, what happens to the sodium? There's also going to be an equilibrium between the sodium, so you're going to have sodium Na and Na plus and the negatively charged protein. Exactly, it'll attach to the protein, but again, there's going to be an equilibrium. There's going to be an equilibrium there, so there's going to be, most of it is going to be in the anionic and cationic form. But some of it will be associated, but very little, because this has a very high dissociation constant, because it's going to be strong. Good question. Okay. And that's how we separate proteins of differing charges. You can use this type of column or this type of chromatography. And so now we have to give a name for this type of chromatography. Does everyone understand it first? Because the name is not important. The understanding is important. Do I need to explain it again? Or you think you have it? Okay. Now let's name this type of chromatography. We call this type of chromatography anion exchange chromatography. And that name should make a whole lot of sense now. anion exchange chromatography. Because what you're doing, you're putting the anionic proteins onto the column, and then you're exchanging those protein anions for another anion. And that's what causes them to elute from the column. Is the name reasonable? Is it a reasonable name? There couldn't be a better one. Now, what if you had, this is a question for the class, what if you had a positively charged protein? Could you use anion exchange chromatography? Exactly. You wouldn't use anion exchange chromatography if the protein were positively charged. What would you use? Cation exchange chromatography. And it's the same, except the beads are going to be negatively charged. How would you elute the protein? How would you elute a cation from the column? Exactly. You can use salt again because the salt is going to have, you're going to exchange the cations in the salt for the cationic proteins. That's one way to do it. What's the second way to do it? Use a base. Because the base is going to cause those protons to be dissociated. Now the cation is going to turn into an anion. It's going to make the protein more anionic or less positively charged. Make sense? Okay. Let us continue. So now we have our protein here. We know it's a negatively charged protein. We have the protein, and then we have this other cation, this other anion X, and an anion Y. How do we get rid of those? How do we get rid of those other anion proteins? That's what I'm ready to explain next. Everybody ready? Ready for the adventure? Let us continue. Actually, I want to put this. I'm going to get rid of all of that. Okay. No, I need this. I need this for my new column. Okay. Going to get rid of that. Wow. Let's see, how do I do this? Okay, there we are. Set to. Okay. I want to put this in here. Okay, so this is what we have. We have our proteins, all of our anionic proteins. Now, let's figure out, well, how are we going to separate those proteins? Now, proteins are going to have different sizes. Proteins are going to have different sizes. And so let's just put some representative sizes for these proteins. Let's say that protein here, we have protein minus, let's say it's a medium-sized protein. Protein X, let's say protein X is kind of small. And then we have protein PX and then protein Y. Let's see, protein Y is a very big protein. Okay. Now we need to come up with a way of separating these proteins. Even though they all have a negative charge, some are big, some are small. Okay. And so what we do here, we have another column, yet another column. See if this makes sense. So we're going to have a column here. Now this is the one that gets students here. This is the concept that gets them. Now on this column, you're going to have these beads. You're going to have these beads in this column. Okay, let me draw my first bead without you drawing it, because you'll have to erase something if you do. And so let's say you have here some beads. And let's say there are 1 million of these beads going across. Okay. And so we have space in between those beads. And also on these beads have little holes in them. And this, I want you to do this here. They're going to have holes in them. holes in these beads. Okay, these beads have holes in them. Okay, now what's going to happen when you put all of these proteins, let's put lots of these proteins here. Well, I'm just going to draw. Okay, we'll do P. This will be P. You have P, and then you have Y here. Y is going to be kind of big. Well, shouldn't have made these that big. The whole point here is that they're just different sizes. They're not drawn to scale here. And there's X. Okay, you have all of these different proteins. Now, when you put these proteins, this mixture of proteins, on this column, what's going to happen? The big proteins, like Y and P. Let's say they're too big to go inside these beads, and so they can travel. So Y is going to be able to travel the short route just between the beads. So this will be P. P can travel the short route and go out of this column very quickly. Y can travel the short route and go through these beads very quickly. But something that's really small like X, it can fit into these holes in the beads. And so X is going to have to travel through these beads, go into these beads and travel all through here. And it's going to take them a long time to get out of these beads, and they're going to eventually come out. And so when you do something like this, your first fraction here, the things that come out earlier, they're going to be your big proteins. And the ones that come out later, these are going to be your small proteins. So the big things is kind of counterintuitive unless you understand what's taking place inside the column. You would think, oh, small things can travel really fast, so the small things are going to come out first. But that's not the case. That's not the case for this. What's going to happen, your very large proteins, because they can go between the spaces and don't have to go inside the beads, they're going to have the shorter route. And so they're going to be able to come through these columns very quickly. So these columns are going to filter the small things and let the big things pass through. Kind of makes sense? Now we're going to actually, in 2 labs, this is a good way. This is actually a very good way. Let's say you have your protein in a very high salt concentration. For like example, let's say in the last one, in our last example, P, X, and Y. Since we had to dilute this from a what type of chromatography did we get these 3 proteins from? Anion exchange. So you're going to have a very high salt. These proteins are going to be in a very high salt concentration because that's what we had to use to elute them. Remember that from the last slide? Now, let's say you don't want it to be in high salt anymore. This is a great way to get rid of that salt because salt particles are very small and they're going to have to travel through these beads. And now, when you finish, the proteins are just going to be in whatever the buffer is you're running it through. Whatever the buffer is you're using as your mobile phase. And so that's a good way to get rid of very small anions and cations, or very small salts. Does that kind of make sense? Anyone? Does that make sense to anyone? And so this is a way to get rid of your salt. So now, all we need to do now is give a name for this type of chromatography. Okay. This type of chromatography has 3 different names. 3 different names, and we're going to name those now. We can call this size exclusion chromatography. Well, I'm going to do it like this. If I just put a C here and don't write the word chromatography out again, would y'all be okay? Would y'all allow that? Thank you. Size exclusion chromatography. And so what size exclusion chromatography does, it excludes the very large particles from the beads. The very large things can't go through the beads. So it excludes them, and so they come right off of the column. Make sense? That's one name. We also can call it gel filtration chromatography. Gel filtration chromatography. And so these beads here, all these beads make a gel. And these gels can filter your very large materials and trap the very small ones. Gel filtration chromatography. And we can call it, another name is molecular sieve. Molecular sieve chromatography. You know what a sieve is, don't you? Like a colander. Like if you're cooking. Like if you say, it's this thing that has, it has all these holes in it. And so basically what that column does, it's like a sieve. It lets the big things through, but it holds the small ones. Make sense? Everyone okay with this? Okay. If you would, put your notes away. Let's see here. Let's see. Okay, where is that? Okay, let's see what we have here by way of questions. What if you have a negatively charged protein that you want to, first, name a globular protein, any globular protein. Tyrosine hydroxylase, very good. Name another one. Dopamine beta hydroxylase, or dopa carboxylase. Okay. Let's say you have a negatively charged protein. How would you separate your negatively charged proteins from your positively charged proteins? You would use high salt later, but what's the name of the procedure? What type of chromatography? Anion exchange chromatography. Very good. Now, let's say you have 3 anionic proteins of different size. How would we separate those anions, those anionic proteins, from one another? Gel filtration chromatography. Okay, last question. Let's say you're using anion exchange chromatography. You have your anion stuck to the column. How are you going to... Oh, 2 more questions. What is the name of the process by which you release your the whatever material you want, you release it from the column? Elution. How would we elute a negatively charged protein from an anion exchange column? We can add high salt or make it acidic. Have a great weekend, you all.